Welcome to The Explainer. Today, we're pulling back the curtain on all those scientific headlines you see. What does it really mean when a study finds a significant result? And, maybe more importantly, is that even the right question for us to be asking?
So let's just dive right in with a number that might surprise you. Some researchers estimate that up to half of all published scientific papers contain errors or inconsistencies. Now, this isn't about fraud. It's about some really deep-seated issues in the system itself that have, well, created a bit of a credibility crisis.
And at the very heart of this crisis is a concept called inferential reproducibility. It's a fancy term for a really simple but powerful idea. Can another scientist look at your data, look at your results, and logically come to the same conclusion? You see, getting the same numbers is one thing, but agreeing on what those numbers mean, well, that's the absolute bedrock of science we can trust. So here's our game plan. We're going to walk through why this crisis even exists, we'll take on the infamous p-value, and then we're going to build a toolkit to help you become a much smarter, more critical reader of science. Okay, so what is actually driving this crisis? Well, a huge part of it starts with a lack of transparency in how research is done and how the results get reported. Now, this slide shows a really crucial distinction. On one side, you've got results reproducibility. That's basically asking, can we get the same numbers again? That's all about consistency or reliability. But then you have inferential reproducibility. That's asking, can we draw the same conclusion? And that's about validity. That's the real goal. Because think about it, you can be consistently, reliably wrong. A massive part of this whole problem comes down to one single number. The famous, and I should say famously misunderstood, p-value. For decades, this thing has been treated like some kind of sacred gatekeeper of scientific truth. So just imagine two studies. They are almost identical. Study A gets a p-value of 0.049. It's hailed as a success, it gets published, people talk about it. Study B gets a p-value of 0.051. A statistically meaningless difference, right? But it's labeled a failure. It gets filed away in a drawer and forgotten. This arbitrary cutoff, this p-value cliff, has completely distorted how science gets done. This obsession is, frankly, absurd. As the researchers Rosnow and Rosenthal sarcastically put it, there's nothing divine about the number 0.05. So why on earth do we treat it that way? So yeah, where did this magic number even come from? You'd think it was derived from some deep, profound statistical truth, right? Yeah, not exactly. The origin story of 0.05 is surprisingly, well, arbitrary. Back in the 1920s, a brilliant statistician named R.A. Fisher just called it a convenient cutoff. Then, later, before we all had computers, it was just a practical necessity because of pre-printed tables. And over time, that convenience just hardened into dogma. It became the law of the land. So clearly, statistical significance isn't the whole story. Not even close. To understand what really matters, we need to talk about the unsung hero of all this, the effect size. See, unlike a p-value, an effect size doesn't just ask if there's a relationship between two things. It tells you how big, how strong, how meaningful that relationship is. It answers that all-important question, so what? Think of it like this. A p-value just asks if an effect is real or if it's just random noise. But if you have a huge sample size, even a teeny, tiny, meaningless effect can be significant. An effect size asks the much better question, okay, but how big is it? It's like this. Significance tells you a light switch is on. Effect size tells you if it's a tiny nightlight or a blinding searchlight. And here's the really crucial part. What counts as a big effect completely depends on the context. A medium effect for predicting someone's attitude is way bigger than a medium effect for predicting their actual behavior. A finding that seems small in one field could be a massive, life-changing breakthrough in another. Context is absolutely everything. Okay, so we know if an effect exists, and now we know how big it is. But that leads us to the most important question of all, right? So what? Does this finding actually matter out there in the real world? This is what we call the search for practical significance. And finding that practical significance is kind of like a three-step process. First, you have to report the effect size. Second, you compare it to what other studies have found. And finally, and this is so important, you translate the finding. You go talk to the people it actually affects to understand what its real-world impact is. So all of this is building toward a better model for science.
And that model requires radical transparency, especially when it comes to talking about a study's own limitations.
And there is a huge difference between a weak limitation and a strong one. A weak one is just this generic token sentence, but a strong one, the kind we should all demand, explains exactly how a flaw might be influencing the results. And it might even offer an alternative explanation. It shows the researchers are being truly, genuinely honest.
Credible researchers are transparent. They give limitations their own dedicated section. They don't just list flaws, they explain their potential impact. They describe, they don't justify. And here's the paradox. A really strong, honest limitation section is one of the best signs of a trustworthy study.
So this brings us to the big takeaway. Now that you know how the sausage is made, what should you actually look for the next time you read a new study or see one of those scientific headlines pop up? Okay, so here's your checklist. First, ignore the headline p-value and go find the effect size. Then, check if it's actually big for its context. After that, maybe even read the limitations section first to see how honest the researchers are being. And finally, always ask yourself the most important question: does this actually matter in the real world? Ultimately, the next time you see a big scientific headline, I want you to ask the better question. Don't just ask, is it significant? Ask, does it matter? Because when we all start demanding meaning over magic numbers, we don't just become smarter readers of science, we actually help make science itself better.